So we kind of already used this idea in the last two examples, I believe. And that was the idea that our g of t was going to be 1. So we could rewrite this as f of tau times 1. And then we would have that equal to the Laplace of f of t times the Laplace of 1. And the Laplace of f of t is just capital F of s. The Laplace of 1 is 1 over s. So it's a nice trick to use when we're trying to figure out what this guy's going to be. And we don't have a secondary function. We actually do have a secondary function. It's just recognizing that the secondary function, that g of t, is going to be equal to 1. So let's talk about integral equations. The convolution theorem in our previous results can lead us to solve something called a Volterra integral equation, which is going to look like this. So notice we're going to have some function in front here, and then we're going to have this guy. This can be rewritten as a convolution. So let's look at how we're going to solve something like that. Let's say we have this, and we want to solve. Your first step is always going to be to take the Laplace. So if we were to take the Laplace here, the Laplace of f of t is going to be capital F of s. The Laplace of 3t squared is going to be 3 times the Laplace of t squared, which is 2 factorial over s cubed. The Laplace of e to the negative t is 1 over s minus a. So s minus negative 1 is a plus 1. And then we need to take the Laplace for this guy. So that's recognizing that this guy is a convolution. We just have to know what our f and our g is going to be. So in this case, our f of t is just the function f of t. Our g of t is coming from this guy, and it's going to be e to the t. So this is really f convoluted with g. So if I'm taking the Laplace of f convoluted with g, then it would be the Laplace of f of t times the Laplace of e to the t. So let's find those. The Laplace of f of t is just capital F of s. The Laplace of e to the t is 1 over s minus 1. Now, this is going to work the same way as what we've done before. We need those f of s's on the same side, and we need to isolate. So if we factor f of s out, we're going to have 1 plus 1 over s minus 1. On the left, we did not change anything on the right. So I want a common denominator here. It's just going to make it easier to isolate. So we're going to have s minus 1 plus 1 over s minus 1. So let's multiply by the reciprocal to get f of s by itself. So that's going to be multiplied by s minus 1 over s. So now we're going to have 6 times s minus 1 over s to the 4th minus s minus 1 over s times s minus s plus 1. So let's do some partial fraction decomposition here. I'm going to write that out. Actually, I'm not going to do partial fraction decomposition here. I'm going to split that numerator. I am going to do partial fractions on this, though. So let's do that over here. So we have s minus 1 over s times s plus 1. That's going to be a over s plus b over s plus 1. So coefficients of s, 1 is equal to a plus b. Constants, -1 is equal to a. So if -1 is a, and we sub that in here, 1 equals -1 plus b, then that means b has to be equal to 2. So we split the numerator for the first one. Now let's sub this in. So we have -1 over s plus 2 over s plus 1. So I'm going to reduce. I'm going to distribute. So there's our f of s. That's as simple as we can go. Now we're to a point where we can take the inverse Laplace. So if we take the inverse Laplace of f, we're going to get f of t. So if we were to take the inverse Laplace here, let's write this out. So we're looking at our formula sheet here, and that matches up with our formula number 3. So we can think about this as a 2 plus 1. So our n is 2. We need a 2 here, and we can compensate with a 2 out here. So that's going to give us a 3, and that's going to be a t squared. If we look at this guy, we can view that exponent as 3 plus 1, and we're going to use that same formula number 3. So we need a 3 factorial here, compensate with a 3 factorial out here. 3 factorial is 6, so that would be a -1 minus t cubed. The inverse Laplace of 1 over s is just 1, and the inverse Laplace of this would be e to the -t. So there is our final answer for that one. So you can see how we took that piece by piece by piece. I want to walk through one more of those with you. Just for fun. So let's say we have f of t is equal to 2t minus 4 integral 0 to t sine of tau f of t minus tau d tau. the key really is recognizing this guy as a Laplace. So just like before, we want to take the Laplace. The Laplace of f of t is capital F of s. The Laplace of 2t would be 2 times the Laplace of t, which is 1 over s squared, minus 4, and then we got to figure this guy out. So this is a convolution. We know this is going to be f convoluted with g. We just got to figure out f and g. So in this case, our f is going to be sine of t, and our g is going to be f of t. So if we want to take the Laplace of that convolution, then it's going to be the Laplace of f times the Laplace of g. So our f is sine of t, so it's going to be the Laplace of sine of t. And then our g is f, the Laplace of f of t. So Laplace of sine of t is 1 over s squared plus 1. The Laplace of f of t is just f of s. So goal is the same as before, isolate f of s, so we need to move all those to one side. Factor f of s out. That's going to leave us with a 1 plus 4 over s squared plus 1. I want a common denominator first before I multiply by the reciprocal. So we're going to have s squared plus 1 plus 4 over s squared plus 1. So this is really s squared plus 5 over s squared plus 1. So then f of s is 2 over s squared times s squared plus 1 over s squared plus 5. And that's really 2s squared plus 2 over s squared times s squared plus 5. So let's do partial fractions again. Wonder if we could make this just a little bit easier. Split the numerator. I don't know if that's going to help us, but let's see. I did it differently in my notes. So this guy's good. Let's deal with this. So we have 2 over s squared times s squared plus 5. So we have a repeated linear and irreducible quadratic. So 2 is equal to AS times CS plus D plus B times CS. I'm just kidding. A is missing an S and an S squared plus 5. B is missing the s squared plus 5. CS plus D is missing the s squared. So we have s squareds, s cubes, s squared, s's, constants. 4 variables, 4 equations. 0 on the left, it's going to be a plus c. 0 on the left, b plus d. 0 on the left, 5a. So we know a is 0. That's nice. And if we know a is 0 and we plug that in, we also know c is 0. That's nice. And then 2 is equal to 5b. So then we know 2/5 is equal to b. And that's nice, because 2/5 is b. Sub in here. D has to be negative 2/5. So then A is 0, that term's gone. C is 0, that term's gone. This ends up being 2/5 over s squared minus 2/5 over s squared plus 5. So let's substitute that in here. So I'm coming down here. So we have 2 over s squared plus 5 plus 2/5 over s squared minus 2/5 over s squared plus 5. Now, I want to put these together. I want to simplify as much as I can before I start doing inverse Laplaces. So 2 minus 2/5 is 8/5. So we have 2/5 over s squared plus 8/5 over s squared plus 5. So now let's take inverse Laplace. On the left, we would just have f of t. I'm going to write the right-hand side out. So the inverse Laplace of 1 over s squared is just t. That's coming from our formula sheet. Now, this guy looks like sine. But remember, this needs to be rewritten as k squared. So we have to be able to recognize that we can rewrite that 5 as square root of 5 quantity squared. But we have to have k on top, so we need a square root of 5 here. We can multiply it in as long as we compensate with a 1 over square root of 5 out here. So that's going to leave us with 8 over 5 square root of 5 sine of square root of 5t. So there's our final answer. The last thing we need to talk about is the transformation of a periodic function. So if we have a function that's piecewise continuous and of exponential order, and it's periodic with a period of t, then we can just apply this definition here. So let's see how we can use that. So notice this guy. We have repeats. Okay, so one cycle is actually this piece. So it's at 1, then at 0, then it's at 1, then 0. And each of those are a length 1. And it just kind of repeats over and over again. So we've got to figure out what is that period and how can we write this function out. So our function, and I'm going to call it e of t. if we were to write one period, it would be 1, as long as we were between 0 and 1. And then it bounces to 0. Here's that second line. From 1 to 2. Period is how often it repeats. It repeats every 2 units. So after 2 units, we see the cycle again. And then we would see it again. And we would just keep seeing that. So if we want to find the Laplace of this, we're going to use this definition. Our Laplace, and I'm calling it E of t. So it's going to be 1 over 1 minus e to the negative 2s, since 2 is our period, and that's going in for that t there. Then we're going to integrate from 0 to 2, that's our period, e to the negative s of t times e to the t dt. Now remember, our e has different values from 0 to 1 and then from 1 to 2. So that means we're going to have to take this guy and we're going to have to split it into 2 pieces. So we're going to have to go from 0 to 1, and then we're going to have to go from 1 to 2. So for 0 to 1, we have e to the negative st. Between 0 and 1, our e to the t is 1. E of t is 1. From 1 to 2, that e to the t takes on a value of 0. So that integral would just be 0, so I'm just going to mark it out. To integrate this guy, we have to do a u substitution. So we would need a negative s here. We would compensate with a negative 1 over s out here. So we have a negative 1 over s. And this would be e to the negative st. And we're going from 0 to 1. So if we substitute in 1, we're going to have e to the negative s. If we substitute in 0, we're going to have e to the 0, which is 1. So I'm going to do some fancy math here. Let's factor a negative out of that. If we do, we're going to have a 1 minus e to the negative s. Negative times a negative gives us a positive. So we have that. So this guy is actually a difference of squares. So let's write that difference of squares out. Here's our top. We have an s on the bottom. We can write that as a 1 minus e to the negative s, 1 plus e to the negative s. Just to confirm that that is correct, it's always good to FOIL back out. So that would be a front is 1, outsides, insides cancel, and the last gives us a negative e to the negative s times e to the negative s. When we multiply and we have the same base, we would add those exponents. So we would get that a negative 2s back. And the reason we would want to do that is that that top and bottom is now going to reduce. So we're going to have a 1 in the top, s over 1 plus e to the negative s in the bottom. So there's our final answer. That would be the Laplace of this particular periodic function. So to find the Laplace of a periodic function, you have to figure out what that period is, how often does it repeat, write it in terms of a piecewise function, set everything up, which is what we did here, and then we have to split that depending on how many pieces we have. And then it's just basic integration.